Today we are going to talk about covalent bonding, and this is page 6 in your chemical bonding packet. This is different than ionic bonding. In ionic bonding you had a transfer of electrons, in which case one atom basically gave away its electrons to another atom, and you get cations, which are positive ions formed, and anions, which are negative ions formed, and they came together to form an ionic compound. Now overall those ionic compounds ended up electrically neutral because the pluses and minuses canceled each other's out. Now covalent bonding is different. Covalent bonding involves the sharing of electrons between two or more atoms, so you're not going to get these strong positive and negative ions. They're usually formed between two nonmetals that have a relatively low electronegativity difference, so lower than the difference between ionic bonding, and that is why ionic bonding involves the transfer of electrons. There is a very large difference in electronegativity. And remember, electronegativity is the tendency of some atoms to pull the electrons towards themselves in a bond. So we have to look at electronegativity difference to figure out whether they are ionic or covalent. Now there's a little bit of a terminology here. When you have an ionic bond that forms a compound, but with covalent it forms molecules. So molecules are atoms held together by covalent bonds, and a molecular substance contains molecules. There are some properties of covalent bonds. They tend to have low melting points and be brittle. They usually have a strong odor, and they usually do not conduct electricity very well. Now there are a couple exceptions to some of those things that I'll talk about in a little bit. Polar bonds form between elements with relatively large differences in electronegativity. Now I say relatively because it's less than the electronegativity difference in ionic compounds, but it's more than the electronegativity difference in nonpolar covalent compounds. So remember, you have to look at that electronegativity chart and get the difference between the atoms to figure out whether it's going to be polar covalent or nonpolar covalent compared to maybe even ionic. The polar bonds have an uneven sharing of electrons. So water is a good example of this. When you have water, the oxygen atom has a higher electronegativity difference than, say, these two hydrogen atoms. So the oxygen would pull the electrons towards itself more in that bond, giving it a partial negative charge, and the hydrogens would then end up with a partial positive charge. So that is polar. You get partial charges. Remember, it's not the same as ionic where you get these full positive and negative charges. These are just partial charges. Nonpolar bonds, for example, exert equal pull on the electrons. So if you have something that is diatomic like O2, obviously they have the same electronegativity difference, so the electrons are shared completely equally. Now they don't have to be diatomic to be nonpolar. You can get other nonpolar bonds that are not diatomic, and remember, you just have to use that electronegativity chart to see which is which. There's different formulas when we write covalent bonding, when we want to represent covalent bonding. So a molecular formula shows how many atoms make up a compound. So methane, for example, is CH4. That subscript goes for the element that comes before it. So it's saying you have 1 carbon and 4 hydrogens. In water, it's saying you have 2 hydrogens and 1 oxygen. Now an empirical formula is a little different. It is the lowest whole number ratio of all the elements in the compound. So benzene is C6H6. Think about these subscripts almost like a fraction. If you can reduce them for an empirical formula, you are supposed to. So that is a 1-to-1 ratio. So that's why benzene, C6H6, that is the molecular formula. The empirical formula becomes CH, 1 carbon to 1 hydrogen. If you have C6H12O6, well, that is a 1-to-2-to-1 ratio. So the empirical formula becomes CH2O. So remember, empirical formula is the lowest ratio. Molecular formula is just showing you how many atoms there are. Now the one that gives you the most information is the structural formula, and it's telling you how these things are bonded to each other. So methane, for example, just showing you that you have carbon basically in the middle and 4 hydrogen atoms bonded to it coming off of it. It uses dashes to represent covalent bonds, which is a shared pair of electrons in the structural formula, and you would need 2 dots to show any unshared pair of electrons. Now there isn't any unshared pair of electrons in this methane example, but we will get into drawing these another day. We'll go over how you draw these and represent unshared electrons and talk about multiple bonds and all that kind of stuff. Now, when you draw these structural formulas, it's easy to double check your work. You want to make sure the octet rule, and remember, I use that word rule kind of lightly because there are exceptions to it, but the octet rule should be satisfied for each element in the compound. So one of the exceptions, for example, is hydrogen. Hydrogen is in that first energy level. It only has one valence shell, or one electron shell, I should say, that can hold at most 2 electrons. So hydrogen is one of those examples where it's not going to get 8 electrons, but it should still have its valence shell full when it is bonding. When you get these bonds formed, remember the potential energy when we talk about chemistry is the energy that is stored in the bonds of a compound or molecule. And what we see is that the bond length plays a big part in how much energy that bond has. So the bond length is the average distance between the nuclei of 2 bonded atoms, just really how far apart are those nuclei. And bond energy is how much energy required to break a chemical bond. Something we're going to talk about more in the thermochemistry chapter, the heat chapter, is that it takes energy to break bonds, right? Energy is stored in the bonds, and if you want to break that, you have to put in some effort, basically. Bond length and bond energy end up being inversely proportional. As bond length increases, for example, bond energy decreases, so the farther away the 2 nuclei are, the easier it is to break them apart. If they're very close together, so short bond length, it takes a lot more energy to break them apart. So we get something like this, and you are not going to have to memorize bond energies and bond lengths or anything like that, but you do want to know the general idea that they have an inverse relationship. So if you look at H bonded to H, hydrogen is the smallest atom in the universe. So it is a very small nuclei, a very small difference between those 2 things being bonded together. Now they have a pretty short bond length, 74 picometers, now that gives you a very high bond energy, 436 kilojoules per mole. Now if you look at the next couple examples on here, you have halogens bonded to themselves, other diatomic elements, and these form a column on the periodic table. And as you move down the column, the atoms get bigger. So what this is telling you is that fluorine bonded to fluorine is smaller than chlorine bonded to chlorine, and bromine bonded to bromine, and iodine bonded to iodine. And what you see is as their bond lengths increase, their bond energies tend to decrease. It takes less energy to break these things apart in general when you have a shorter bond length. And you have hydrogen bonded to the halogens. And what you see is as you get larger and larger halogens, so going down that column, you get longer bond lengths and you get lower bond energies. Again, you're not going to have to memorize the bond energies or the bond lengths. Just know that as one increases, the other one decreases. They have an inverse relationship. Depending on the bonding type, we can also get a general trend for boiling points. And if you look down at the bottom here, ionic compounds tend to have very high boiling points, much higher than polar covalent, which is higher in general than nonpolar covalent. So we're going to talk about why that is. Now there are a couple exceptions to this. And to be honest, we're not going to really have to worry about the exceptions. I just wanted to point them out. These 3 things listed here, diamond, graphite, and C60, which is a type of fullerene and also called a buckyball, they tend to have very, very high boiling points, somewhere around 4,000 degrees or so, 4,000 degrees Celsius. So why is that? And I have another one listed here, a nanotube, which is also formed by just carbon atoms. So because these things are all made of carbon, they are covalently bonded. And I was just saying ionic compounds tend to have very, very high boiling points, but these carbon-based molecules also have very high boiling points, and it's really just because they are so large. So in general, there are exceptions to that general trend that covalent molecules have low boiling points. We're not really going to worry about the exceptions much. We're going to stick with the general rule of thumb, which was listed here, where you have ionic compounds as being the highest, nonpolar covalent compounds as having the lowest boiling point, and the polar covalent somewhere in the middle. Right, so don't worry about the exceptions. I just kind of wanted to point it out that there are some. So what is going on here? Why is it that you get difference in boiling points depending on what kind of bonding it is? And it has to do with intermolecular forces. Now think about what that prefix means, inter. Inter means between, and intra means within. So there's different things. There's intermolecular bonds and intramolecular bonds. Intermolecular means the attraction between two or more molecules. Intramolecular means the bonds that are taking part inside the actual molecule or compound. So ionic bonds, polar covalent bonds, and nonpolar covalent bonds are the intramolecular forces. But what we have to talk about for boiling points, figuring out why things boil at different temperatures, is the intermolecular forces, things that we haven't talked about yet, and they are the attractions between two or more molecules. So dipole-induced dipole is the first one. It is the attraction between polar molecules. So when you have a polar molecule, one side has a high electronegativity difference, and that's what this yellow one would be, and that's why it has a partial negative charge. It is pulling the electrons towards itself more, so the other side of the molecule is going to have a partial positive charge. And what happens here is when you have a bunch of these molecules near each other, the partial positives are going to be attracted to the partial negatives. And then that is an attraction. It is not a full bond by any means, but it is an attraction, and that is the type of thing that has to be broken for these molecules to boil. The London dispersion forces, and they have to do with the constant motion of electrons. So if you see the word motion, you should think London dispersion forces. And when these electrons are moving, right, so you might start off with a symmetrical distribution, but when these electrons are moving, they might every once in a while congregate more on one side, and what you get is referred to an instantaneous dipole, where this molecule might not usually have a dipole, but you might get these instantaneous dipoles form. So you get this partial negative charge formed on the right-hand side of this molecule, which means the left-hand side is going to be partial positive. So you get what's referred to as unsymmetrical distribution. And what happens is that unsymmetrical distribution may impact another molecule and cause that one to have an unsymmetrical distribution. So this partial positive charge might kind of influence the electrons on this side to then congregate mostly on one side of that one, which then gives that one also a partial positive charge. The main thing with London dispersion forces, like I said, if you have a hard time telling the difference between these things, London dispersion forces has to do with the constant motion. So if you see motion, think London dispersion forces, but it has to do with unsymmetrical distributions of electrons. Hydrogen bonding is the last one we're going to talk about, and it occurs when a hydrogen atom that is in a electronegative atom, so something that has a relatively high difference in electronegativities, is attracted to the electronegative atom on another molecule. So water, for example, is a good example. If we look at this water molecule that's in the top left, oxygen has a higher electronegativity difference than hydrogen, so it gets that partial negative charge, which means the hydrogens then get a partial positive charge. Now, if you have other water molecules in that general vicinity, what happens is that partial positive charge on the hydrogen gets attracted to the partial negative charge on another water molecule, specifically on the oxygen. And then one of their hydrogens can be attracted to another oxygen atom that has a partial negative charge. Now overall, this hydrogen bonding, again, is not a full bond. It is just an attraction. So even though it says bonding, like in hydrogen bonding, it's just an attraction. And just one of these attractions does not have much energy to it at all. But imagine if you have a glass of water where you have trillions and trillions of these water molecules, you would get a lot of hydrogen bonding, and then that would end up having a pretty big effect on the properties of that thing. All right, what you want to do is work on page 10 now, and if you get a chance, you can watch